Good afternoon, everyone. Thanks for being here today. Thanks also for those connecting from remote. It's my pleasure to welcome today Mr. Masayuki Sato, who is visiting us from Tokyo, from Japan. So thanks for traveling and making the effort. It's a real pleasure to have you here in the series of seminars for the PhD program for aerospace engineering. So. Mr. Sato received his PhD in aerospace engineering from the University of Tokyo in 2009. And he has been developing his career since 1997 in the National Aerospace Laboratory of Japan, JAXA, which might be familiar for you. His research interests are fundamentally on design of robust controllers for different types of vehicles, both manned and unmanned. And he has been in the last years a principal investigator of a project between European Union and Japan, in which they have been testing this type of controllers for ARPAs, for UAVs. He's going to be talking today about the lessons learned in controller design in the last 20 years. As for research, he's serving as associate editor for several international and domestic journals, including EEE and IFAC conferences and journals. So, floor is yours, and thank you very much for having here.
Thank you. Thank you. Does everyone hear me? Okay. Okay. Thank you. So, my name is Masayiki Sato. As he said that, and I'm working for the JAXA. That is a counterpart of ESA and ONERA and CNES or NASA, something like that. And also, German Aerospace Laboratory, that is an DLR as well. So, but many guys usually focusing on space topics. But to be honest, I'm not totally interested in space. But I had a small interest in a football game. I'm so sorry last night. You may know that I didn't say anything. I'm not so sure that which team won, but good relief for me. That anyway, sorry for that. And so I just talk about flight control design, and of course my research interest is focusing on control theory using a linear matrix inequality that is called the LMI or convex optimization problem. So could you raise your hand if you're interested in the LMI or convex optimization? Thanks. Just one. 2 or 3. Okay, thanks. Thank you. Yeah, because how to say, usually many flight control engineers don't care so much about LMIs or convex optimization problem. But I think, in my feeling, it might be better to pursue such advanced techniques to design a sophisticated flight control design. So, but in this talk, it is better. I found it is better to focusing on flight tests and flight control design using conventional flight control techniques. Okay, so I think the topic is very familiar with all of them, and we didn't say we just focusing on the very conventional techniques and the flight control design. Okay. So, yeah, here myself, maybe 15 or 20 years ago, something like that. So this aircraft is called as MUPAR Alpha, Multi-Purpose Aviation Laboratory. But here these characters are written in Greek. I cannot pronounce at all, but my boss named this aircraft as MUPAR Alpha. Alpha represents airplane. Oh, thanks so much. So, and using this aircraft, we implement uncertified flight controllers for using this aircraft, because this aircraft has a research fly-by system. So we can implement your own designed controller to this aircraft, and you can test flight. So this is very good test bed for examining control performance. Okay. And we also developed several types of UAVs, and this aircraft is called as the unmanned area radiation monitoring system. That is, you may know, I believe you know that we had a very severe earthquake about 10 years ago, and we had several problems from that Fukushima nuclear power plant, and radio contaminants spread out from over there. This area is just 7 kilometers away from the nuclear power plant, and of course there is a radio contamination spread out over there as well, and so many people are evacuated from the place, and there is no man, and there is just animals over there. But many people want to get back to their hometown. So we must examine how much radiation affects over there. So of course, if you can go walk the way and you can check, oh, radiation power is not so good, not so powerful, so we can see there. Of course, but if there is some spot with radiation power is so strong, you cannot get there. But if you measure over there, you will be radiated. It's terrible. So to escape such a tragedy, this aircraft is developed. That is, radiation power is monitored from the sky. So that is a very convenient, that is a very safe way to examine the radiation power around the Fukushima nuclear power plant. Okay, but during this development, we found that there is a runway. To find the appropriate runway is very hard, because as you see that this aircraft has a conventional type. So we need maybe about 200 meters runway to take off and landing. Is it possible to find such a long runway? No. Indeed, it's very hard to find the appropriate place for landing and taking off place. So another solution, another solution to find such a big place is to invent vertical aircraft, VTOLS. That is quad tilt wing unmanned aerial vehicle. In short, QTWAV we say. That is a vertical aircraft like an Osprey. So we have no need to find a wide area to operate this aircraft. But of course, this aircraft is operated by just an electricity, so we need further development to use in practical cases. Okay. But when we talk about these topics and we give some my lessons and learned from these experiments. Okay. So, yeah, this is mine, and he is one of my bosses. So we first gave some, the background of this talk. That is, usually control engineers, like including me, want to implement newly developed controllers. But sometimes, too much complicated to implement practical systems. But usually, my bosses want to implement well-established controllers. That is a PID controller. So PID controller, why do you use PID controller? That is very simple and very easy to tune appropriate gains. But sometimes, slightly poor performance might be introduced. Okay? But usually, they want to implement very established controllers. So the objective, we'd like to compare the objective. That is, we would like to implement newly developed controllers to realize good performance. Oh, that's reasonable. But of course, there, the first objective, the priority objective is that reduction of development risk. Okay. But of course, we also want to develop good aircraft as well. That is, they want to develop a good aircraft, but first priority is steady development. So, objective is the same in the both sides, but different priority leads to a very severe conflict sometimes. So that's why we usually invent or design very conventional flight controllers using PID controllers. After that, we replace the sophisticated ones. So during this process, we need to obtain bosses' trust. That is the main message from this talk. So, of course, it is very important to pursue the both ways. That is developing a new control technology and developing a good test bed is both necessary to survive this competitive world. So in my experience, that is steady pursuit and acquisition of new technology are crucial to survive this competitive world. And in particular, for example, in my case, that my research interests, as I said, that include control theory. So I continue to pursue my new technology related to these topics, robust control and gain schedule control, something like that. But if you want to demonstrate your controller's practicality, it is very important to have flight demonstrations with your design controllers. Otherwise, usually, how to say that, many workers in industry usually say, oh, your controller looks very nice, but how practical your controller is? How do you implement? That is a very critical point in my sense. So flight facility is very important to demonstrate your controller's performance, your controller's effectiveness compared to the conventional ones. Okay. So to this end, indeed, I did a lot of admin works to maintain our facilities. And so if you get into some research or academia positions, I strongly recommend to do a lot of admin works to keep your facilities. Okay, so this is just a message for master course students. Okay, and in Japan case, that is, you may know that. Have you ever heard of MRJ's name? No. Oh, you thanks so much. Yeah. Yeah, MRJ is a short abbreviation of the Mitsubishi Regional Jet. So, and that was renamed as Mitsubishi Space Jet. I remember that. So that, anyways, Mitsubishi Heavy Industries has launched a regional jet, but its development has stopped. Why? Because they wanted to implement a new technologies as much as possible, but they cannot get the certification from the authorities. So they stopped the development. That is very terrible for Japanese communities and Japanese researchers of them. But we'd like to emphasize that if you want advance your technologies and to do that and your related works, you must first do a very obsolete but very well-established technology should be used to develop something. That is a very bad example. So Mitsubishi Heavy Industries has stopped, and I guess we cannot restart its development program forever because we have already spent a lot of money, and I guess the authority has already abandoned the process, I think. So in my belief that it is very important to give a very steady development for the future. Okay. So, but this is a little bit historical topic. Japan, you may know that Japanese, World War II, in the World War II, we lost against United States and many countries. And but at that time, Japan had a very some advanced technology related to the aerospace. So, in my understanding, one of the examples is a mechanical gain schedule control in World War II. So this picture is pulled from the Wikipedia, and this is a Zero Fighter here. Zero Fighter uses mechanical gain schedule techniques depending on aerodynamic pressure. Really? I didn't heard of that before, maybe 2 years or something. So usually, many guys has already know the dynamics of the flight control. That is, usually aircraft usually controlled by an aileron, rudder, and elevator. That is, they are using the aerodynamic pressure to create moments. Okay. So here, high aerodynamic pressure, if you fly in the high aerodynamic pressure condition, then with very small deflection angles with and elevators create large moment. Okay, so if large moment created, this might happen. Yeah, pilot-induced oscillation. Of course, the cause is different in this case. That is, this PIO was reported to cause by the actuator limit. That is, there is some limitations of actuator movement. So this limit introduced such an accident. But this similar oscillations will be introduced by such a large moment. For example, if pilot moves like a stick like this way, so if the aircraft moves very heavy, severely, so then, oh, it's too much. So usually pilot reacts the motions. But again, the reaction is too much, so there is pilot oscillation like this. So to solve this problem, how did they solve? Flex barriers used. That is, the flex barriers produce small deflection angles because they are extended due to the high aerodynamic pressure, like this way. Okay, so thus maneuverability is almost kept, regardless of aerodynamic pressure. That is amazing for us. That is, this is indeed a mechanical gain scheduling control technique. Of course, nowadays we can easily solve by using software's advanced control techniques, but that is an amazing technique in the World War II. So, but you may know that why zero fighters lost their advantage. Of course, there are several reasons. That one of the reasons is that I read I read several books and I found that they say that engine manufacturing was not matured. So thrust power was not sufficient to opponents like in a Hellcat, like this one. And of course, we have another problem, that is structural problem. That is the fuel tank is very fragile. So to reduce the weight, the fuel tank is easily firing without blitz restriction and so on. And of course, the maximum operation speed is reduced due to the insufficiently strong structures like this one. So, but in my opinion, that is most crucial factor is lack of humbleness. That is usually, how to say that, Japanese might be slightly arrogant because their fighter had a lot of advantage compared to their opponent. So they didn't continue polishing their techniques. So in my understanding, this is very important part to be humble. So you may know that in Japan, in late 1990s, that we had a big bubble economy and we have a lot of monies, but you may know that the bubble economy has already gone away, and the Japanese is still struggling in the economic crisis nowadays. So I think that Japanese people might be arrogant, so it is very important to be humble. So my general message, this is a very general message for the in particular master course students. That is, be humble and keep trying to acquire new technologies. Okay, of course that is a kind of a spiritual talk. Sorry for that. But after that, I'd like to talk about the flight control design and flight testing. Okay, so first I'll give some topics related to in-flight simulators. That is, using the mu alpha. So in this flight test, we design flight control using the HVT control techniques. Of course, nowadays, HVT control is slightly obsolete, but maybe 15 years or something like that, HVT control was still active, very hot topic. So at that time, usually it is not allowed to implement HVT controllers, but due to some reasons, we indeed implemented HVT controllers to practical this actual aircraft. Okay, so after that, I talk about flight control design using the UAVs And in this case, we design conventional gain scheduled PID controllers, and after that, talk about the UARMs, unmanned area radiation monitoring system. In this case, we incorporate preview control in addition to the conventional PID controllers. Of course, at first, my boss was not allowed to implement this controller, preview control, but we give, after several steps, we got a permission to implement preview control. So I just talk about this issue. Okay. So, have you ever heard of the infrared meter? Could you raise your hand if you heard? Okay, nobody knows. Okay, what is infrared meter? Okay, so that is an aircraft that achieves an extension of ground-based simulator to the flight environment, and it's real-world case. It's a conceptual description. In other words, IFS infrared meter is an aircraft that can mimic other aircraft characteristics in flight. So how do we do this? How does mu alpha mimic other aircraft characteristics? Of course, you may know. You know that aircraft characteristics like CL alpha, CL, CD, and such coefficients are ruled by its shape. Of course, we cannot change shapes without authority permissions. How can we change? Yes, flight control did it. That is, using the appropriate flight controller design, this feedback loop, so we can, for example, we can measure some attitude and attitude rate, something like that, using these attitude signals and using the pilot commands like this way. And pilot commands create modeled dynamics motions that is given by ZM. And using these signals, we can create appropriate control signal UP to drive this aircraft to mimic other aircraft motions. So that is an infrared meter controller. That is called as an infrared meter controller. But if we design appropriate controller to mimic other aircraft, this aircraft moves like other aircraft. Okay. So infrared meter was used to demonstrate and to examine handling characteristics for newly developed aircraft. Okay. This is an animation here, but this is an actual video recorded in the flight test. And in this animation, that model aircraft is shown here. That model aircraft motion is calculated by an onboard computer with right-hand side pilot input. Okay. Of course, this aircraft indeed sat on the right-hand seat of a research aircraft, and they control wheels and pedals, throttle levers, and so on. Using this control input with appropriately designed controllers, using just the aileron, elevator, ladder, thrust, and our mu alpha moves like this aircraft. Okay, mu alpha motions here obtained in a flight test with applied HPG model matching control. Okay. Okay, I'll show you a video. Yes. So there is no sound, sorry for that. But indeed, here the F2 pilot, that's a fighter pilot working for the Mitsubishi Heavy Industries. And we had a good collaboration with Mitsubishi Heavy Industries at that time, and he came to my facility site, and he get on our mu alpha, and he control our aircraft. And in this case, this aircraft is approaching to some regional airfield, and sorry. Sorry. And you see that there is an airfield over there. Of course, this pilot doesn't see the motion of this aircraft. This pilot just sees outside from this aircraft. So this is an offset landing approach. That is there is a runway there, and offset approach is set, and he's trying to keep this straight away. And at that time, at a certain different distance from the airport, that is an maneuver is created by this pilot. Yeah, of course, slightly your angle is slightly different because we cannot control 6 degrees. That we just have 5 degrees, so we just control forward speed, vertical speed, and roll angle, and pitch angle, and yaw rate only. So we cannot control yaw angle. So that is why there is some difference here. But indeed, in this flight, even with only feedback control, the model matching is almost realized. Because here the bank angle, yaw rate, the deviation of the localizer, and the longitudinal motion is here. That is forward speed and vertical speed, pitch angle, and altitude, and glide slope deviations. So the red lines represent models calculated by onboard computers, and the actual flight test result was drawn by blue lines here. So as you see that, of course, sorry for that the units are removed due to the confidential issues. But as you see that there is overlapping almost here, as you see that. So, but usually, flight control engineer usually ask me that why were not feedback controllers used? Because feedback controllers change gas response, so which may make pilot feeling different from the normal aircraft motions. So to prevent such an effect, customer required us to use only feedback controllers. But in feed-forward control design, we use advanced design technique, engine control design. And furthermore, we obtained trust from pilot in JAXA. So that is a very good occasion for me to obtain the JAXA's pilot trust. After that, for example, we implement weird controllers for pilots. That is, in this case, we use gain schedule controllers designed by LMI. So the matrix size, the controller size is very huge. Like the state space model has about maybe over 300 values or something like that. That is a very unconventional for pilots. Okay, but after obtaining pilot's trust, we easily implement our my designed controllers. So in that case, for example, in this case, usually, how to say, the scheduling parameter is affected by uncertainties. In this case, the scheduling parameter is set in speed, equivalent speed, but usually equivalent speed is measured by pitot tubes. So we have some uncertainty in the measured equivalent speed. So this effect sometimes apparent here, like this one. But if we design some appropriate gain schedule controllers by considering the effect of uncertainties, we can easily design a good model matching control like this one. So the objective is to coincide the blue lines with red lines. Here, but the left-hand side see that you see that there is some discrepancies. Okay. So, okay, this slide and the next slide is a little bit complicated, so I would like to skip a little bit. Yeah, that is. So this slide is. Sorry. Indeed, this is a flight test video. So after implementing our designed controllers, we had a flight test, and during this flight, pilot moves control, that is like heaving and going down. And during these motions, roll and sway speed commands are created by flyby computers. Okay. But speed is controlled by the pilot maneuvering like this way. So during this flight, gain scheduling flight control was implemented, and we did have a test result as shown before. So during flight, we can see some good sceneries, Mount Fuji's, and sometimes we can see submarines, and we can also see the Yokohama Naval Base as well. But of course, this is a business. That is my duties. This is not fun, but anyway. So after that, I had a good international collaboration work with Andres. Sorry for that. Indeed, we have EU-JP international collaboration work for FTC, photo trend control, and FDD, photo diagnosis, and photo detection and diagnosis. Yep, using these with these guys. Here, Anders, as you see. So, lessons learned from 20 years working on JAXA, MIP Alpha. So, good work should be done within customers' requirements. And after achievement, trust would be obtained, and then another chance is come. Thanks to, in my case, that the vision, indeed. I had a vision project in EU-JP project, and this is, I owe a lot to Andres, so thanks so much. And however, even within a severe constraints, keep trying to acquire new technology or to apply new methods in order to advance your skill. That is a very important message to myself as well. So, I guess time is running. Sorry for that. But so next, we'd like to go to the to go to the QTW and U forms. So, as I said, the QTW is a conventional aircraft. That is like this is the tilt rotor is head up, up sideways. So in this case, thrust creates vertically, and in this case, the thrust creates the forward speed. So to fly this aircraft, we must design a PID controller like this way, very conventional SCAS structure, but that is scheduled by the tilt angles. So seeing is believing in this. I show the video. That is, after designing an appropriate gate schedule controllers scheme like this one, we implement our designed controllers, and we had a flight test. At that time, we didn't implement speed control, so speed control was made by a ground pilot. So I just called out the current speed and the target speed to adjust throttle lever. Of course, in this case, I just show a successful flight like this one. But we had, sorry for that. And how did we design the controllers? That is a very simple technique. That is, robustness is implemented to classical schedule controller, like using the multiple model approach. So this is very classical. So that is, we first set cost function like this one, and we set supposed models representing uncertainties. And using this cost function, we just minimize using the gains to be designed. This is very simple combinations. But of course, we usually have some constraint to be satisfied. That is also implemented like this one. Of course, in this case, we must slightly revise the cost function like this way, using the weighting coefficients, lambda. And we also extend this formulation to the case in which the disturbance effect should be incorporated. So in this case, maximum functions here and max functions here. And for this augmented max functions, we must minimize the cost function using the k. That is a very simple formulation, and we can easily obtain the practical controllers like these formations. Of course, see that the bank angle and the pitch angle are controlled. So blue lines and red lines and black lines are almost the same. So you see that very good performance are obtained. But as you see, there are some large discrepancies happened here, like this one. So these cannot be overcome by gain tuning. So I think advanced design should be applied to overcome these topics, these issues. So in this subtopic that is a good potential, I found that the good potential for the conventional PI controllers, that is the structure of gain schedule controller can be determined reasonably, and a very simple structure is very welcome for implementations and on-site tuning as well. And yeah, as I said, easy implementation is very appreciated by many researchers. Okay, and easiness of on-site design is also appreciated by many guys. So yeah, I just want to say that, but to this end, for the successful flight, indeed, we did many tunings. It is very tedious work, and it is laborious work. So I think it is better to advance our technology to the future. So, but I also understand that the conventional PID controller works very well. But in this case, there is some small accident. That is, when the remote control radio was lost, the aircraft falling down. But the SAS system indeed works well, and the SAS rescued this aircraft. So this is that in this, on that day, there was a very beautiful sunset. Here you see very beautiful. But here, falling down indeed. Yeah. In this case, only SAS works. Stability augmented system only works. But in the control augmented system doesn't work. But even in that case, SAS works very well, and their SAS rescued this aircraft indeed. So good work should be having involved in the QTW work. Good work should be done within the customer's requirements. And after achievement, then another occasions will come. But of course, in this case, development, significantly advanced technology were not applied, but the development was used as a chance to obtain boss's trust. So I'd like to just go very rapidly on the last topic. That is, we implement preview control for the altitude control for this conventional type UAV. Of course, this is a diagram representing the longitudinal motions control. So this is that there is SCAS that is controlled by, the SCAS is composed of the pitch rate feedback and the pitch angle feedback, something like that. And we also implement the speed control using PID, and altitude control is also designed as a PID controller. That is very conventional. But in this case, if the altitude has altitude command has changed like this way. So we had a big error that is about 30 meters difference between the altitude command and the actual altitude. It's very huge. So how do we solve this problem? We just implement very simple preview control. Of course, the technical details is skipped here, but this is very simple. We just estimate the altitude command in the future, and we create the revised altitude command using these appropriate gains. Okay, so at first, preview control was not implemented because the boss didn't allow me. But after that, after the successful flight of the QTW, the boss admitted. So this is here. The right-hand side is actual flight test result around the hilly areas. So of course, that's the maximum error in the climb phase is just a 7 meters difference. This is that here the difference is 28 meters. So it's about quarter. It's much reduced compared to the conventional ones. So I would like to wrap up my presentation. That is, be humble and keep trying to acquire new technologies, and trust can be obtained if obligations are completed within customers' requirements. But it is better to keep doing your best to advance your skills. And of course, that in the QTW case, how to say that, both the trust is the consequences of the successful flight of the QTW. And this leads to preview control implementations to this conventional aircraft. So indeed, we implement several advanced control technologies after getting boss's trust and the JAXA's pilot trust. So I think it is very important to be humble and keep trying to advance your techniques. So that is the end of my talk. Sorry, a little bit overlapping. So